Hello, my name is Justin, and today I'm going to be presenting Lab 2 of EE178. In this lab, we're going to be implementing a full adder using two half adders. As you can see here, this is our schematic for our half adder diagram. We have one XOR gate and one AND gate. And then over here we have our truth table where we have two inputs and two outputs. Over here we see that when both inputs are 0, the sum and carry are equal to 0. When there's one input, when there's an input that is equal to 1, the sum will always be 1 and the carry will always be 0. And when both our inputs are equal to 1, our sum will be 0 and our carry will always be 1. Over here is our half adder expression, and our half adder expression for our sum and our carry. And now we're going to be seeing our Verilog code. So first we have, sorry about that. First we have our half adder module where we have our variables. We have our two inputs, A and B, and we have our two outputs, sum and carry. And over here we have our half adder expressions where we have our XOR gate of A XOR B equals to sum, and we have our AND gate where A and B equals to our carry. Next we have our test bench, which we'll open up right here, where we have our inputs. Sorry, this should be the other way. This should be our inputs, and this should be our outputs. Yeah, so we have our outputs of sum and carry, and we have our inputs of A and B. And in this line, we instantiate our half adder module. And over here, we have our 4 test cases where we have where we have 4 combinations for our inputs. And now we will run our simulation. And over here we see that, let me see if I can make this a bit easier to see. Yeah, so over here we have when on this side panel we have our 2 inputs, and over here we have our 2 outputs of our simulation. So when A and B are equal to 0, our carry and sum will also equal to 0. And when we have one of our inputs equals to 1, our sum will equal to 1. And likewise, we will have, as you can see here, when one input equals to 1, our sum will also equal to 1, and it doesn't matter which input is equal to 1. Moving on, and for our last test case, when both our inputs A and B are equal to 1, our carry will equal to 1, whilst our sum will equal to 0. And now, since we know that our simulation matches our truth table, we will now run our synthesis. Yes. And we'll run, and then we'll also implement the program. And while that is running, we can also see that our schematic will match our diagram that we saw earlier. as you can see here. Yep, as you can see here, our two inputs. Our diagram matches to our theoretical. And next we'll run our implementation. And as we're running that, we can also check our constraint file, where we'll set our LEDs N20 and P20 to our carry and sum. And we have free switches where we'll have A, B, and C set to R17, U20, and R16. We only really need our two. We really only need two switches for our inputs for our half adder, but we also have our C, our third component for our full adder next. That I will show later. So next we can generate our bit stream. Yes. Let me make our camera a little bit bigger for you guys. Alright, our bit stream generation has finally completed. So next we can open our hardware manager, and we can then open our target and connect it to our backboard right here. And next we can program our device. And now we can see that now we can check whether if our program works. So first we have our two switches, our two inputs right here, switch 0 and switch 1, and using our we can check whether if our truth table whether if our blackboard matches our truth table here. So when we have A and B equals to 0, we see that our two LEDs, LD0 and LD1, do not light up. But when, let's say we have B, or we have one of our inputs, we'll see that LD1 is our sum. It will light up. Next, if we have our other input, our sum will also light up. Next, if we have both our inputs light up, our carry will be set, while our sum will be equal to 0. So knowing that works, we can now switch. We can now switch to our full adder. Over here we have our we have our full adder diagram, where we have two full adders, and we also have one I believe it's one OR gate, and we also have our carry out, and we have one XOR gate too. Yep. So, and we also have a third input where our sum is A XOR B and XOR C. So now we'll head towards our truth table here, where we have our free inputs, and since we have free inputs, that means we have 8 combinations that we need to implement. And on this side we have our two outputs, our sum and carry out, as it matches our block diagram here. And down here we have our full adder expressions, where our sum is A XOR B XOR C, while our carry will be this equation, C times A is for B plus AB. Yep. Oops, sorry about that. So now we can close our hardware manager here. And I have already set up our full adder module. So in that case, we can just sorry about that. We can just go straight to implementing our full adder. So over here we have so here we have our full adder module. It has a similar layout to our half adder module, where we have our variables, our variables, and so here we have our free inputs A, B, and C, and we also have our two outputs. But this time we need to define some wires where we have half sum 0, half carry, half sum, and half carry, and this matches our block diagram from earlier. Next, we can instantiate our two half adders in our block diagram, and on this line we define our final carryout value and our final sum value. Moving over here to our test bench. Here we have our outputs when we have our inputs, and here we are instantiating our full adder right here. And in this section, we are we have our 8 test cases, and we are also using the same constraints file from before. So here we can run our simulation. Yes. Sorry about that, my computer had an issue. So now we'll continue to run our simulation. Let me actually, but I've already loaded up our simulation, so we can just go straight to that. So over here on our side panel, we have our free inputs A, B, and C, and we have our two outputs, sum and carry. And you see that, let me bring up the file again, where we'll be seeing if it matches our truth table right here. Let me just zoom in a bit. Okay, not too much. There it is. That's good. So first, when on over here on the side, when A and B are when we have all of our inputs equal to 0, our sum and carry will also be equal to 0. But when we have let me bring this to the side a bit. When we have one of our inputs equals to 1, then our sum will equal to 1 as well. And this will be true, and this will, when we have 2 of our inputs equals to 1. Let me see if we can get 1. Yes, when we have 2 of our inputs equals to 1, our carry will also equal to 1. Oops, that's too far. And yes, that was our previous test case. And we will try to get, let me see if I can get a, yes, there it is. When all of our inputs equals to 1, our carry and sum will equal to 1 as well. Perfect. And now that we know that our truth table matches our simulation matches our truth table, we can now we run a synthesis and implementation. Yes. And while our synthesis is running, we can check if we can see that our schematic from our Verilog code matches our full block diagram on our left here, and that's how you know that our Verilog code is should be sufficient enough. Next, for run our implementation. And our implementation is, now that we know our sorry about that, we had some technical difficulties, but now that we know that our implementation and synthesis is completed, we can now program our blackboard. Over here we have our constraints file where we have our two outputs, carry out and sum, set to our two LEDs, LD0 and LD1. And we have our free inputs A, B, C set to our free switches over here. And next I'll bring up our truth table, where we will be testing each case. When all of our inputs are 0, our sum and carry out will be 0, and we can see that that's true in this case, where none of our LEDs are lighting up. And when we have one input set to 1, we have our sum equals to 1, and we'll be testing all three inputs. Okay, now we know that works. We can set two inputs equals to 1, and when we have two inputs equals to 1, we have our carry out set to 1, while our sum equals to 0. And we can test it for all combinations, for example. Alright, now that we know our two inputs also work, we will now test our final case, where when three inputs equals to 1, our two outputs, sum and carry, are also equal to 1. This has been EE178, Lab 2. Thank you.